Welcome to Part 4 of this week's online lecture. In Part 4 we will discuss the effect of relaxing the harmonic approximation and using an anharmonic oscillator model. So we need to relax our harmonic oscillator approximation and introduce what is known as an anharmonic oscillator model. Real molecules do not obey Hooke's law. They are not truly harmonic oscillators. We need to introduce a more realistic potential function to reflect two important properties. One, the molecules dissociate if the bond length is much larger than the equilibrium bond length. And two, that the nuclei themselves repel each other when the bond gets much smaller than the equilibrium bond length. So the potential is much steeper than you would predict in the harmonic oscillator at small bond lengths. Remember that the harmonic oscillator also implies that the nuclei can go through each other, which really doesn't make any sense. So therefore the potential energy surface that we really want is one that becomes steeper at small internuclear distances, but becomes shallower at larger internuclear distances, and those are to reflect repulsion and dissociation. One of the simplest functions that has been introduced to represent these properties is known as the Morse potential. This black line here is meant to illustrate a true potential. So again, we are talking about potential versus bond length. We identify once more the equilibrium bond length as being the minimum of our potential function. And we can now identify a new property of the potential, which is the dissociation energy. And notice that again there is a subscript E indicating equilibrium. So this is the dissociation energy from the equilibrium position. There is something rather strange about this particular dissociation. It's because we can never directly measure it, because molecules are never at the bottom of the potential energy well. The lowest energy that they can possibly have is the one in which they are in the V equals 0 level, which is slightly above the bottom of the potential energy well. So we never really measure D sub E. We always measure the dissociation energy from the V equals 0 level. Then we have to do a little bit of maths to determine what dE might be. So this is the representation of a true potential. Here is a harmonic potential. And what I'm trying to illustrate here is that one of the reasons why it works quite nicely in low vibrational states, that is when V is small, is because at the bottom of the potential energy well it describes quite nicely a true potential. In part 3 we saw mathematically why this is so. As long as the displacements are small, the harmonic oscillator will work quite well. A Morse potential does have the right kind of shape, but it won't perfectly match the true potential. It doesn't have all the theory that underpins the true potential. So in general, it is not quite as steep as the true potential as nuclei get closer and closer together. And at larger internuclear separation, well, it can go either way. It can come up to be steeper than the true potential, and sometimes it is shallower than the true potential. Here I've drawn it as shallower than the true potential. So what does the Morse potential function look like? Well, it looks like this. We've introduced an exponential term into this expression. So let's have a quick look to see if this makes any sense. Do we get a minimum? Well, at the equilibrium position, R is equal to RE. So R minus RE is equal to 0. So the exponential term will be equal to 1. So the term in brackets will be equal to 0, and so the potential is 0, and this will indeed be a minimum. How about when R is large, as it tends to infinity? When R is infinity, R minus RE will also be infinity, which will mean that the exponential term is 0. So the term in brackets is equal to 1, and so therefore the potential is equal to the dissociation energy dE, which is just what we wanted. At values of R less than RE, the potential increases exponentially, which is an improvement over the harmonic oscillator. So the Morse potential has the properties we are looking for. It does have a dissociation energy associated with it, and it does have a minimum at R is equal to RE. Our dE is the equilibrium dissociation energy. There is this other parameter A, which is a property of the molecule, so it changes from molecule to molecule. As A gets bigger, the potential gets steeper at both small and large internuclear separations. In essence, it is a fitting parameter, so there is no significant theory that underpins what value it should have. It is just something that we get from observation. We had a wonderfully easy potential term to fit into our Schrödinger equation when we were looking at the harmonic oscillator. That was just -1/2 kx squared. Now we have this term with an exponential factor in it, and we've got to substitute that into the Schrödinger equation instead. But there is a solution, and indeed it is an analytical solution. One of the reasons why Philip Morse developed this potential in the first place is because there is an analytical solution for this kind of function in the Schrödinger equation. And the analytical solution looks like this. It is very similar to the one we had for the harmonic oscillator. Remember that for the harmonic oscillator we got this term here, just the first term. What the Morse potential brings in is this second term. Notice that this one goes as v plus 1/2 squared. So the first term goes as v plus 1/2 and the second term goes as v plus 1/2 squared. So you can imagine, as we go to very large values of v, for which the harmonic oscillator doesn't work very well, this second term becomes more and more important. Its value becomes larger in comparison to the first one because it is going as v plus 1/2 squared rather than v plus 1/2. In general, of course, the nu e chi e factor is a small number. This second term is generally a small perturbation to the vibrational energy. For small values of v, you can sometimes ignore this part, in which case you get back exactly what we had for the harmonic oscillator. If this second term is very small, i.e. insignificant, then we get our harmonic oscillator solution. And that has to be right, because we know fundamentally that for small values of v it should tend towards the harmonic solution. It doesn't have a choice. Whatever model we came up with to describe anharmonicity had to have the property of tending towards the harmonic solution for small v, and so the Morse potential does have that property, which is another reason why it was chosen. When we were discussing the harmonic oscillator, we used nu0 rather than nu e. They had the same value for the harmonic oscillator, so I deliberately used nu0. Here I'm deliberately using nu e. Again, nu e is not something we can measure in the spectrum. It is not something that is measured, it is something that we have to derive by fitting this equation to our spectral data. It is a hypothetical frequency. It is the frequency the molecule would be vibrating at if the molecule was at the bottom of the potential energy well. When it is at v equals 0, it is not going to be vibrating quite at that frequency. I should point out, however, that nu0 is the frequency of the photon absorbed when the molecule goes from v equals 0 to v equals 1. We will see later what the relationship is between nu0 and nu e. So this is the equilibrium vibrational frequency around the equilibrium position. It is a kind of hypothetical frequency because we can't be at the bottom of the potential energy well. This chi e is what is known as the anharmonicity constant, because essentially it is this term which is defining the perturbation we are applying to our harmonic problem to take into account anharmonicity. The chi e itself is unitless, but the product with nu e, of course, has units of wave numbers. Let's have a look at vibrational frequency then. We can determine a force constant for the Morse potential simply by taking the second order differential of our function. So if you differentiate it twice and calculate it when the bond length is equal to Re, this is the value that you will come up with. We can substitute this into our expression for vibrational frequency. So the vibrational frequency will look like this. Nu e is equal to 1 upon 2 pi times the square root of 2 times the dissociation energy from the equilibrium position times our A parameter squared all over the reduced mass. So how has this changed things? This is our new vibrational energy term where we take into account our anharmonicity. All it is a perturbation to our harmonic solution. And this here was our harmonic solution. When V was equal to 0, the energy, the vibrational energy, was equal to a half nu 0. When V was equal to 1, our energy was equal to 3 halves nu 0, and so on and so forth. Let's see what happens when we include anharmonicity. We can see that the energy at V equals 0 is now a half nu E minus a quarter nu E chi E. When V is equal to 1, it is equal to 3 halves nu E minus 9 quarters nu E chi E. When V is equal to 2, it is equal to 5 halves nu E minus 25 quarters nu E chi E. And when V is equal to 3, it is equal to 7 halves nu E minus 49 quarters nu E chi E. The anharmonicity constant is a positive number, so we are always taking away a positive number from the harmonic result, and so the lines are getting closer and closer together. You can see that this term is going as V plus a half squared, and so it is getting larger and larger as we go to larger and larger values of V. And our lines thus are getting closer and closer together. So this is a kind of result that we expected, that as we go to higher and higher vibrational energies, our levels are getting closer and closer together as we approach the dissociative limit. In terms of the spectroscopy, now that I know the energies of each of the levels, I can calculate the frequency of any transition. So the fundamental frequency would be a transition from V equals 0 to V equals 1. How does the result differ from the harmonic solution? Well, it will be 3 halves nu E minus 9 quarters nu E chi E minus a half nu E plus a quarter nu E chi E, which is equal to nu E minus 2 nu E chi E. With the harmonic solution we had nu E, but now we've got nu E minus 2 nu E chi E. We will discuss this again in just a little while. So the fundamental thing is that the levels are not equally spaced. They are getting closer and closer together. As we approach the dissociative limit, the levels are getting closer and closer together. We can imagine that there is potentially a maximum vibrational quantum number beyond which it will dissociate. In fact, we can calculate what the Vmax is by differentiating our vibrational term expression. For any total vibrational energy, the potential energy curve defined the limit of compression and extension of the bond, well, at least classically. The potential energy curve is confining the vibrational limits of compression and extension. We can see that these are the limits here for the V equals 0 state. The molecule can vibrate from this bond length to this bond length. Beyond these vibrational limits, we go into the classically forbidden region, where the potential energy would be greater than the total energy of the molecule, which would imply that the molecule has negative kinetic energy. The average bond length in any vibrational level can be considered to be the midpoint between full compression and full extension. Again, at least in a classical sense. Classically, our molecule cannot have a bond length smaller than the limit imposed by the potential energy, because if it did, then its total vibrational energy would be smaller than the potential energy, which implies, as I just said, that kinetic energy would be negative, which makes no sense classically. Because the potential energy is not harmonic, the average bond length for any vibrational level is getting longer and longer as V increases. Because of anharmonicity, the bond length is getting longer and longer the closer we get to the dissociative limit. and this has an effect on the vibrational frequency. The vibrational frequency does depend a little, at least, on which vibrational level you are in. However, I would like to make it clear that the molecule is vibrating at very nearly the same frequency, no matter which vibrational state it is in. The reason why the molecule has more vibrational energy in higher vibrational states is because it is stretching and compressing over a wider range, and this requires more energy. This is the end of part 4 of this week's online lecture. Please continue on to part 5.